So for question 9.43, we're asked to draw 3 different isomers of the dichloroethylene, which is C2H2Cl2. And first things first, isomers, basically what they're asking for, they have the same chemical formula, but where they differ is their arrangement in where those atoms are in space. Around, and we'll see what that means in a second. And so, where to start, right? If we count up the valence electrons that we have to work with, we would see that we would need to have a carbon-carbon double bond between both carbons, and then from there we're just going to place the remaining elements around these carbons, keeping in mind that carbon wants to form 2 bonds, or 4 bonds total, so 2 more bonds. So we have 2 hydrogens, and sure, we'll place both of those on this side of the double bond, and we'll place the 2 chlorines on this side of the double bond. And then we need to fill the octet of chlorines. So carbon has 4 bonds, hydrogen has the 1 desired bond it wants, chlorine has the 1 desired bond it wants, and everything has a full, has as many electrons as it wants. So this is one isomer of the dichloroethylene that we're asked to draw. This is basically one arrangement, one possible arrangement for this molecular formula. And we need to remember also that, right, because we have a carbon-carbon double bond, there's no free rotation around this carbon-carbon double bond, so there's no way for this carbon to spin around, putting, you know, the chlorine up here and the hydrogen down here. That cannot happen. So that's what makes this an isomer. It's locked in this conformation. So in order to make a different isomer, we have to change the location of where that carbon is, and it makes it a different molecule. And so, you know, just for example, when we make that change, we still have our carbon-carbon double bond, but we're going to move the position of one of the chlorines. And so this is a new molecule because we have both chlorines now on the opposite side of the double bond. They're not on the same side of the double bond. These 2 molecules cannot interconvert between each other because of this double bond. There is no free rotation, so this would be isomer number 2. And you might think, oh, okay, so if I just switch the places of the hydrogen and carbon, or hydrogen and chlorine, and to go from 1 to 2, then if I do that again, that should give me the 3rd isomer. And we can draw that isomer. But you'll notice, right, if you just switch the position of that 2nd chlorine, if we switch sides of that 2nd chlorine, you'll notice that there's an awful lot of similarity between this isomer and the first isomer we made. You notice that both chlorines are on the same side of the double bond, so it's identical to the isomer number 1. So this is not a unique isomer. It's basically just flipping this whole molecule 180 degrees. But one isomer we haven't considered, we've considered moving the chlorines. We haven't considered the number of chlorines on each carbon. And we'll notice that in both the previous isomers we had 1 chlorine on each of the carbons. Now let's put both chlorines on 1 carbon and the 2 hydrogens on the remaining carbon. And this would be the 3rd isomer now, right? This is a 3rd structure. It's different than the previous 2 structures. And, right, we can't draw any other isomers because the only other place we could shift these chlorines is switching them, but it's the same molecule. So for this molecule, there are only 3 available isomers we can draw, right? Same chemical formula, different arrangement of where the atoms are in space. And it's all due to this carbon-carbon double bond that makes these, you know, these 3 structures cannot interconvert. They're 3 different isomers of the same molecular formula.